Hi, I'm John Neary. I lead the HOK Facades Group in New York. The structural Terra Cotta mullion is a collaboration between HOK facade specialists, TriPyramid Structures, Boston Valley, and Gartner Permasteelisa. And for us, the opportunity to participate in the ACAW program represented a chance to test a concept we hadn't seen anyone try before, to use terra cotta as a compression element in a composite structural facade system. And the reason this is worth trying is that it could present an alternative to conventional facade systems. And while there are good reasons for doing things the way we do, namely with aluminum and steel and glass mullions, we all agree constantly that we must find new and more sustainable ways to build. And this kind of research and development is the way this will happen. Terra cotta is low in embodied carbon by weight, and it is relatively inert thermally, and significantly, it is non-combustible, unlike plastics and timber. These two properties offer an aesthetic sculptural potential as a facade material. They enable a mullion that bridges the plane of the glass, existing outside on the facade and inside the building, connecting the two realms and animating the building surface. Our team includes members of HOK Facades, Structural Engineering, and Architecture, TriPyramid Structures, Designers and Mechanics, and Gartner Permasteelisa, managers, engineers, and fabricators, all working with the Boston Valley team. Credited photography and video were created by Patrick and Marzena Bernard. Terra cotta is most familiar in contemporary facades as rain screen cladding, plank and baguette, some cast shapes. There is growing evidence of interest in the sculptural qualities, including color of terra cotta as an alternative to the ubiquitous glass grid, as a handful of recent facades such as SLM's 28 and 7, which I wasn't aware of when we started this project, illustrate. Our first concept was to create a kind of truss with terra cotta in compression and stainless steel cords providing tension to resist bending force imposed by wind. So that's what these are. Thinking of this as rethinking the mullion led to considering the earliest examples, such as a Reims cathedral from around 1230 AD. It is a structural element resisting bending under wind pressure by its mass and its depth. We wanted to capture its sculptural quality in a terra cotta mullion that spans the boundary between inside and outside. Traditional pre-modernist terra cotta facades were representations of stone architecture in less expensive materials. The Woolworth building's explicitly Gothic style included carved terra cotta sculpture that mimicked stone ornament. This cladding was wired and clamped and pinned to structural backup steel. It created the illusion of structural surface. On Sullivan's buildings, the plastic essence of clay became a medium for the animating force of imagination, represented by organic patterns based on the dynamic growth of plants and the structural expression of classical and Gothic architecture. It was an abstract expression of structure. With its plastic ability to achieve intricate molding and carving, as in Sullivan's ornament, terra cotta has been used to create surfaces of a richness never matched except in carved stone or cast bronze. With its similarity to brick, we expected terra cotta would have significant structural capacity and compression. Combining terra cotta and compression with pre-stressing, steel tension reinforcing was done by Eliade d'Este in his famous projects in the 1970s, where tile forms the surface of thin pre-stressed shells. The principle is similar to reinforced concrete, especially thin ferrous cement is used by Peter Rice for the sunshades at the Manil collection. But casting is a different set of processes from the assembly that we envisioned. Rice also explored the combination of tensile rods acting in concert with blocks of stone in compression in at least two projects, including the arches at Expo 92, a view of which is shown here. After Boston Valley agreed to the idea for our project, we asked Michael Mulhern and Jeff Anderson of TriPyramid if they would join in the design effort to test the idea. Their work as the premier designers and manufacturers of structural facade components began with the tension structure at the Louvre Pyramid, which I also worked on. The first step was to have chief engineer Nate White analyze the forces in a hypothetical mullion of 20-foot span and 5 to 10-foot spacing. We assumed a single length of terracotta and a wind load of 30 pounds per square foot. Boston Valley asked Professor John Carty at Alfred University to help us with testing information on the material, and he provided tensile strength of 4,300 psi and a compressive strength of 11,660 psi, similar to high-quality concrete. Project manager Matt Bull began modeling some versions of the MULLION. An initial concept with two sets of pre-stressing rods, one inner and one outer, was simplified with the introduction of structural stainless steel plates, shown here at the base and the top, at the joints between the sections of terracotta, which are limited to 5-foot lengths by current production capabilities. In the event of one rod or one half of the terracotta failing, load would be transferred to the other half. Access to the rods and the fittings is provided by a stainless steel cover, which protects and expresses the tension element. The next step was to test the material under pre-stress load to see how it would act in the event of an impact. We were afraid that it might explode. Impact loads were applied to test samples under a range of pre-stress forces by crouching behind the plexiglass storm door and swinging the steel rod over to whack the terracotta. I believe that Matt was standing about 30 feet away since he forgot to operate the camera on the tripod, while intern Dylan Schwally was delegated to swing the rod. The results were encouraging as the material seemed to almost self-heal when cracking occurred, though pieces did fall off the surface. Nate White declared it tough as nails, and no interns were harmed in the testing of this concept. While discussion with TriPyramid was going on, we were working with Boston Valley studying the shape of the MULLION and how the structural vertical would connect with the rain screen infill transom pieces at the sill and the head. Victoria Araskina did iterative modeling studies exploring the shape of the MULLION and the cast bosses at the corners. We tried to unite those with the verticals visually while avoiding the reading of a static frame. We asked Roberto Bicchiarelli, North American lead concept designer of Gartner Permasteelisa, to help conceive how the parts would be assembled as a facade that would meet high performance criteria for thermal resistance, air and water infiltration, and movement. He brought with him Bernhard Rudolph, head of engineering of Gartner, Germany, who did initial sketches of glazing frames supported on the plates at the joints in the MULLION. Gartner and Permasteelisa have extensive experience with terracotta, as on the recent One Vanderbilt Tower with material from Boston Valley. Roberto agreed to have Permasteelisa construct a visual mock-up which would demonstrate the technical feasibility and the aesthetics of the concept. Boston Valley pre-construction manager Andrew Prius developed the terracotta profiles to make the pieces conform to requirements for extruding, casting, and assembly. BV and TriPyramid collaborated on analysis of the shapes for strength and stability. Initially, we had imagined the terracotta MULLION with a natural burnt sienna color, but wanted to incorporate the beauty of glaze as well. The terracotta color glaze combines the two. We had thought about exposing the tan base as resembling the French limestone of the original inspiration at Reims, but without the fossils in their texture, we decided against that. As a result of the imponderables of different kilns at BV and in Kansas City, where Andy Brayman made the original samples in the glaze, the final color has a subtle violet hue. BV made a range of samples to see the shape of the MULLION with different colors, including the faux granite found on older buildings, including Woolworth, so we could test the reading of the profile. TriPyramid developed assembly drawings for the MULLION based on a process for pre-stressing the continuous high-strength stainless steel rods that hold the sections of terracotta together. Springs at the top of the rods maintain the compression force against thermal expansion or deflection, which is severely limited to L over 5,000. The rods pass through the plates, which spread the force evenly through the clay sections, and are connected with couplings at each joint to allow for replacement of damaged sections of terracotta in theory. Permasteelisa engineers and fabrication experts did the structural calculations and shop drawings for the mock-up. You can see here the insulation that we located between the two halves, interior and exterior. They modeled the mock-up assembly, including all the terracotta clips, support angles, fasteners, flashings, and the viewing enclosure. It was an object lesson in the expertise of the fabricators to see our complicated modeling of the anchorage connections and flashings simplified to what is built. You will see photographs of the mock-up in a moment. With our final design in hand, we have done a basic comparison of the embodied carbon equivalent in the Terra Cotta mullion and a number of more conventional mullions compiled on the slide by Marie Achalaban. Terra Cotta has a low embodied carbon equivalent value by weight compared to the common materials used for mullions, aluminum, steel, and glass. Timber is lower, but it's not so common. Also compared here is precast reinforced concrete. Preliminary assessment indicates a savings in embodied carbon equivalent compared to the others, except for timber. In discussion with TriPyramid, we estimate we could reduce the weight of the Terra Cotta mullion by as much as 50% with fewer joints and a spar scheme to spread on the tension cords, to get a spread on the tension cords. This type on the slide is small, but next to each image are gray bars that graphically represent the relative quantity of embodied carbon content, evaluated according to the University of Bath ICE database. Aluminum, which is over here, and steel over here are much higher than the others. The Spar concept with exposed exoskeletal tension cords was our initial thought for combining a pre-stressing tension component with compression member Terra Cotta, and was the real impetus originally for asking TriPyramid if they would help. This kind of arrangement would afford the greatest reduction in overall weight, but it also is more difficult, would be more difficult to build. Terra Cotta mullion is designed as two separate redundant pillars, each with a stainless steel tension rod internally, which is this, and with a thermal separation between the outside and inside, connected by stainless steel plates at the joints, which are low conductivity elements, roughly 15 times less conductive than aluminum. To achieve the same kind of expression of depth on the exterior of the glass without thermal bridging, an aluminum fin would need its structural cross-section entirely inside the glazing line, and any exterior material would be entirely decorative, adding to the embodied carbon total. To achieve the expression on the exterior with a conventional assembly clad with Terra Cotta, not pre-stressed, would require a steel member such as an HSS on the interior to take the wind and dead load of the glass, with the exterior profile supported on brackets, resulting in significantly larger cross-section than the pre-stressed assembly and more material overall. We imagined the concept for the prototype extending to a unitized curtain wall system that would have the aesthetic qualities and potential embodied energy benefits of the mullion. Rain screen cladding on the spandrel of a unitized frame allows for externally insulating the frames, which usually degrade the effective U value of the curtain wall. Terra Cotta inherently suggests relief, depth, density, and variable densities, supporting different modulation and scales across the facade as we envision it. In this section, you can see what is a metal insulated spandrel, which sponsors a rated fire-safing assembly at the slab edge and a version of a stack joint here engaging one level with the level above. The Terra Cotta on the spandrel is a rain screen. We learned recently that Sullivan's Buffalo Guarantee building originally had a kind of kinetic facade with awnings that tenants apparently operated in groups, creating a large-scale pattern similar in spirit to our sketch for the Terra Cotta curtain wall, which could be less or more decorative as desired. This is an abbreviated look at the fabrication of our mock-up, where the concept is tested for constructability and how it really looks and feels. At Boston Valley, special tools and machines combine with handcraft in creating the Terra Cotta pieces. We talked about the idea of wabi-sabi, the intentional incorporation of imperfection in the modeling of the boss elements, which had complicated geometry. This came up again when we saw that the new pieces have crazing in the glaze, which is only visible with dust on the surface when they're new. At TriPyramid, the tension components are milled, tooled, and forged in stainless steel. As with the clay components, precise machine work is combined with skilled craft. Together, the stainless steel tension elements and the glazed Terra Cotta compression body of the mullions represent a synthesis, a machine and handmade. The armature for the actual facade assembly, including vision glazing, was fabricated by Permasteelisa subcontractors according to engineering and shop drawings by Permasteelisa engineers. Sealant compatibility, adhesion, and staining pre-testing was done by Dow Silicone. Ironworkers from Local 580 in New York brought to Buffalo by Gartner and a team of carpenters guided by Permasteelisa fabrication managers Leo Flores and Khalil Ramani built the mock-up at Boston Valley's facility. The ironworkers erected the mullions and installed the glass in a few hours. This is Gus, the foreman. The mullions are sized in cross-section for spans and spacings twice what we have on the mock-up, but the effect of the proportions, the color, the combination of the terracotta and stainless and glass is visually successful even at this scale, in my opinion. The completed mock-up is photographed by Marzena Bernard. We left the cover off on the interior to make the tension elements visible. The design calls for epoxy between the stainless plates and the terracotta, which would be covered by sealant on the exterior, maybe on the interior. The tolerance on the plates is almost zero. The effect is a celebration of the joint, to use a famous phrase. The milled capital suggests the presence of the cup springs under the surface and also states our express interest in the aesthetic qualities of the overall assembly and the composition of the parts and the combination of materials and surface textures making up the whole. A group at HOK investigated some ideas based on the terracotta mullion to see where it might lead, including this diagonal grid by Francesco Moreno, which would be made up of pre-stressed mullions and node connectors. We plan to pursue the terracotta mullion concepts further in the future. Please feel free to contact me or Boston Valley with any questions. We'll put you in touch with members of the team. Thank you.
John, thank you. It's a wonderful presentation, and I know we will have a little bit more time in the panel, fabrications panel, a little bit later. I think this is a really interesting example. There was one question that I thought would be useful, John, maybe just to reflect on here. It is, was the embodied carbon of the fittings and extrusions included in the carbon footprint calculations?
I'm sorry, was the
embodied carbon of the fittings and extrusion included?
Yeah, what we calculated on that sheet is the weight of the terracotta and the stainless steel. And in all of the examples, we have not included anchors or glass, which would be a constant in any wall system. But yeah, we have about 900 pounds of terracotta and 200 pounds of stainless steel in that version that's mocked up, which if we could eliminate some of the horizontal joints, would go down significantly in terms of fittings and stainless.
John, thank you very much. We'll carry on this conversation in our panel on fabrication a little bit later. And thanks again for really bringing this to ACAW this year. I think it's raised the bar on many levels.
Well, we want to thank you all for having us. It's been a really great experience. It's been gratifying to see the initial ideas, somewhat ratified by just the willingness of the participants to explore it. And the mock-up is exciting for all of us.